Hello, everybody. This is Professor Ma, and this is the sections on using Taylor expansion to do approximation calculations. The tool we're going to use is the remainder theorems, and so let's review what the main remainder theorem says. We started with the differentiable formulas, and we'll calculate its Taylor polynomials, and we're going to expand at the point x equal to a. And then we're going to find out, use the Taylor polynomial to approximate what's the value when I put in b. Okay, so here's the remainder theorems one more times. And so one more time, this P of n of x itself is given by the formula sum up to n, the polynomial, you take the kth derivative of the function f divided by factorial, and then you expand this around the point to the kth power, k equal to 0 to n. Okay, so this is this polynomial. And this is the function f of x. And we're going to take a point B and plug in here, which is a B. Of course, going to take a B plug in here, which is f of B. And then we're going to compare this polynomial value versus f of B. Of course, they're not the same, and that's what the Taylor remainder theorem says. Oh yeah, that's the errors follow this particular formula, and then you look at the formula and say, what is C? C is somewhere in between A and B. We don't know where it is, but there's a number C that fits these descriptions. Okay, so how good the polynomial, quote unquote, approximate the value at B depends on how many terms, what degree of the polynomial P is. The higher degree it is, the smaller the yellow part is. That's the error, because the higher degree of the polynomial we use, approximation is better, and the yellow part is the tail end, the error terms that we didn't use. Okay, so the way we're going to approximate things is we're going to specify what accuracy we want the approximation to be. And then we're going to guarantee that accuracy that we want, the accuracy range, bigger than the yellow part. Okay, and the yellow part is the error. So, and I want to make sure the error is no more than the specified accuracy. And then I want to find a polynomial that will do the job. That yellow portions, this yellow part is smaller than the specified accuracy. Okay, for certainty. So in order to clarify our language, we'll first talk about what do you mean by first decimal place accuracy, second decimal place accuracy, etc. Okay, so first place decimal accuracy means the error is less than 0.05. So we follow this formula. And second place decimal 0.005, 20, and the three decimal place means the 3 zeros. Okay, and you say, what does this language came from? All these things. So, well, it came from basically, if we talk about round off, for instance, if I want to round up 2.534 versus 2.528, and now I said if I round it off at decimal, and both of these will round off, remember from before, they both will round off with 2.53. We drop the 4, we round up the 8. And this round off answers to 2 decimal, round to do the second decimal place, will guarantee the accuracy, this answer is within 0.005. This is where the language comes from. Okay, so the usual rundown methods will give the correct places of decimal accuracy, decimal places of accuracy. Okay, so here's example. Here's a Mach polynomial, so Mach series of e to the x, and we're going to plug in the number 1 for x to find out what e to the first power is. Okay, and want to make sure that the answer you get from the polynomial, its answer is within 0.00005. Okay, remember, if I keep adding these xm plus 1, so first let me plug in 1, so it's 1, 1, 1, 1, so plugging 1, the next one is 1 over m plus 1. Basically, the question is, so this is all the tail end of the approximation. Basically, the formula is ask you says, use the Taylor remainder theorem and guarantee so that you can guarantee me and tell me what degree of the polynomial has to be so that you can guarantee me this part that you omit, okay, must be smaller than 0.5. Oh, one more zero. Okay, your error that you're going to have using the front to approximate the real answers has to be less than 0.00005. Okay, so that's what the question is. Well, by the remainder formulas, the remainder at nth degree is given by this formula. So if I'm going to plug in 1, so I'm going to get e to this power c m plus 1 for some number c between 0 and 1. Okay, and now remember, I want this number to be less than these 0.005 things, one more zero to the 4th decimal place, right? And so I'm going to be generous, okay? That is, I'm going to find the numbers. First, I'm going to replace the c by 1, okay? So I know the remainder, which is this term, certainly has to be less than 3 divided by m plus 1, okay? And now I want to find out for one number n, so I can, n is the degree of polynomials. So I can check, I can set n to be any degree I want to, because I want to decide which degree I want, so I can do the calculation. But the stipulation is that the error term is this much has to be smaller than 0.005. Okay, so this inequality gives you the degree of the polynomial you will need to do the approximation, such that that little arrow terms at the end, the yellow part, is small enough, guaranteed smaller than this number. Okay. At this point, you say, well, gee, how do I solve this? N plus 1 is it's a factorial. How do I solve this inequality? Well, we don't really have to solve it. You can just plug in a number, like let's say put 5 in there. Okay, by trial and error, see which number n will fit. When you go up to 9 factorial, you will find out, oh, this calculator is 3 divided by 5 factorial, 3 divided by 6, it's 3 divided by 7 factorial, see how big it is, and then keep doing this. It doesn't go, pretty soon over here, you will find out that 3 divided by 9 factorial, it will be less than the prescribed number, which means n is 8. Because n plus 1 is 9, so n is 8. In other words, the 8th degree polynomial approximating e to the x will guarantee the error no more than 0.00005. Okay. So, and this sum, it's approximately this much. Okay. Give us the security knowing that the first 4 decimal places it's within 0.0005 of these decimal expansions. Okay. If you need more accuracy, higher accuracy, you need to hire more people, build bigger machine, pay more money to give you more better approximations. Okay. Here's an example approximating cosine. Okay. Up to 3 decimal places, and the things we want to remind you. So we're going to first of all expand around x equal to 0 using Maclaurin expansions, and 3 degree has to convert it into radian measurement. Okay, 100 pi over 180, 3 times 3. Okay, and here's Mach polynomials. So, and here is the remainder terms. I want this remainder, I want to find a number n, what degree of polynomial I supposed to what n supposed to be, which degree, so that this remainder thing is less than 3 decimal 0.005. Okay. Of course, this part I can replace by 1 because cosine number goes out -1 to 1. So therefore, I get a numerical inequality which I can check. Okay, between I can check for n using a calculator and try n go to 3, 4, 5 until the answer is less than 0.005. And I say, oh, okay, n is 3, 4, whatever. But n2 is sufficient. Okay. And so then you only have to use the first quadratic second degree and for n equal to 2, the polynomial. That's sufficient approximation, guarantee you to the accuracy to 3 decimal places. Okay. Now, the derivative of a Mach series is the Mach series of the derivatives. So if I take the derivative of the sine, the Mach series, the first one, you find out you get cosine. Okay. So and if you integrate it, you get minus cosine. So in other words, this basically example illustrated, if I integrate, if I take the derivative of a power series of a function, it's going to be the derivative power series, it's going to be the power series of the derivative. The same thing for integral, okay? Now, one of these things, one of these is more interesting is the integral. Why? Because for the integrations, there are a lot of functions that it's not the integral are not elementary. So we don't know what the integral of for instance, sine x over x and stuff like that. Okay, so here's basic theorem we're going to use to talk about how do we approximate functions that are not elementary. So here's where we talk about really talk about examples of non-elementary functions. Okay, so read these particular statements. Basically tells you can take derivative of power series and take integral of power series. This is just what I just want to talk about, derivative relationship between derivative and integrals. Okay, so here, integral of sine x over x is an important function. Okay, it shows up in application that you want to add these summations of this wiggly line. Okay. And so you try to take the integral of it, but it's not elementary. There's no nice simple formula that derivative is sine x over x. Okay. Even though I can plot it. It's not defined as 0, but I can of a sine, but I can plug it in. So again, this is one of the case where it has you can plug in a 0 to be 1, and then it's a continuous and the differentiable functions. Okay. And so I don't know what this function is, but I know what the power series of antiderivative. I can integrate the antiderivatives. I can do. I take the antiderivative of the power series of sine x divided by x. Sine x divided by x is taking the sine of x power series divided by x. You cancel the x, and then you get this alternating series. So integrate that. I can integrate term by term. It's the same as integrating this power series. So I pull the coefficients out and add 1 to the powers is 2k plus 1 and divided by 2k plus 1. And that's the integral of the integral of these dx is comes out this part, right? And the rest you just pull out. So therefore, I arrive at what the antiderivative or what the power series representations of the antiderivatives. Okay? And the reason because there's no simple finite elementary way of expressing what antiderivative is. And with these, we can calculate, for instance, plugging, you can say, oh, what is, oh, by the way, and this is what for each, if you plug in from 0, integrate from 0 to x, and you plug it in, then you will find out this is what the series gives you the antiderivatives. So for example, another non-elementary functions is e to the minus x squared, integrated from 0 to the minus 1. Okay, you cannot integrate these, and you don't know what is non-elementary. Okay, but I can expand first the exponential formulas. Okay, so plugging e to the expansion for e to the u or e to the x, plugging x squared, so now I get a bunch of even power, alternating even power. Okay, now I want to integrate these. So I integrated the power series, and so I integrated the series term by term. Okay. Integral of 2n plus 1, right? The degree is 2n minus and 2n plus 1, and then the 2n plus 1 divided by the coefficient 2n plus 1. So that's the integral of the integral part. Okay. The n factorial is just a constant state sum there. Okay. Now, we want to make sure when we plug in 0, okay, when we plug in 0, I get 0. When plugging 1, I get this particular series. Okay. The front part. Okay. So now the next question, given these particular patterns, okay, what degree of polynomial, which is the same as what are numbers in the front that I need, so I can guarantee the sum, this part of sum or the tail part of this is less than smaller than 0.005. So that the part that vanish off to infinity. Okay. This we need to notice, this is a convergent alternating sequence, okay, because of plus and minus, okay, and it is actually a convergence absolutely, okay. If you put absolute value, this actually also converge, but that's another story, okay. So the question is, how many terms should I add so the part at the end over here is less than 0.0005. Okay. Okay, so one of the things we're going to use here is about the decreasing alternating sequence. Notice, okay, if I here's an alternating sequence that's decreasing. Okay, so if I add them all up, whatever the answer of this is, this answer has to be smaller than the first terms. the absolute value of the first term. Okay. What does that mean? It means if I were to add up this part, which is also a alternating series, okay? So then this part, if I add it up, and then this part is going to be smaller than the very first number, 1, 9 times 4 factorial, okay? So the sum of decreasing alternating series is always smaller than the very front term, the first one. Why? Because immediately you're going to take a chunk of that away, so the sum is going to drop, but you're going to compensate a little bit back, okay? But not as much as what you take away, and then you keep doing this. So that's what this particular facts is addressing, okay? So in other words, I'm asking the same questions as where should I start? So the first number, I only have to look at the first number is less than 0.0005. Because if the first number is less than 0.005, I know the entire thing is less than 0.05. And it's pretty easy to check, okay? You check this and you find out that the first number on the list is this one over here, is less than 0.005. Hence, we can say add that up, and that will give you the accurate definite integral up to 3 places. Okay, 3 decimal places. So that's it. Okay, this is how we use the remainder theorems to nail down how many degree of the polynomial is needed to do the necessary accuracy to achieve prescribed accuracy. Okay, bye-bye. And